Hello, I want to discuss automatic video segmentation. In general, the task is as follows. If we have videos and a metric, we need to evaluate the contribution of an element in these videos to this metric. This task is already easily solved by pre-trained networks, when the networks are trained on a set of pre-known objects and learn to identify them in videos with high accuracy. But what if the set of elements in the video is not known in advance? After all, preparing the dataset and training the model on a set of elements is quite a laborious task, and the market situation can change faster than it can be done. I propose automatic segmentation of previously unknown objects, followed by their clustering, that is, grouping, and then finding correlation with the required metric, that is, determining what contribution to this metric is made by a particular object in the video or in the group. Now let's see how it works on test videos. Then we'll discuss the principles of operation, then we'll move on to the system's work on a real task, and finish with interpreting the results. For the test, I prepared multiple videos containing simple geometric objects arranged in various combinations and configurations. Also created an imaginary metric, the contribution of which we will evaluate these objects. After identifying video objects, we need to cluster them. We accomplish this by assessing comparable characteristics in these objects: edges, colors, shapes. The vector of such features lies in a 2048-dimensional space, which is quite difficult to visualize in a flat image, so we will use PCA or principal component analysis to extract the most important features that characterize these clusters. As we can see, the objects grouped into clearly distinguishable clusters. Now let's analyze the contribution that each of the clusters makes to our imaginary metric. To perform this task, we will calculate the average metric value for all videos, the average metric value for each individual cluster, and analyze the percentage by which our cluster contributes or decreases relative to the overall average value of the metric. We see that some clusters give a noticeable increase in the metric. For example, the 4 stands out from all. We observe videos where there's a group of 4, memorize their names, and go to a table with an imaginary metric for analysis. And it is evident that the videos that contain the numeral 4 possess the highest values of our hypothetical metric, as we can clearly observe and ascertain. Thus, the algorithm's efficiency becomes evident. We have learned to identify individual elements that make the most significant contribution to the metric we are evaluating. Let's see how the algorithm works on a real task by uploading several videos from the creative test. These are 10 videos that participated in the unity test, and as a metric, we will choose the install rate obtained as a result of these tests. Since the test was done in one place and at one time, it's possible to confirm the consistency of these results. We observe that clustering has already provided us with a significantly wider and more diverse range of clusters. And let's assess the impact of these clusters on the install rate. It becomes obvious that in more complex videos, the interpretation of the results becomes more complex. For example, some objects may be repeated, or it may be difficult to describe what this object represents. Hence, interpreting the results is crucial and must be done exclusively by a qualified individual. What conclusions to draw from the information received is already up to the creative producer or another person who has decided to conduct such an analysis. But the main conclusions that I would like to derive from the application of this technique are that it truly enables us to evaluate the impact of factors, objects, and video components that were previously unknown on the metric being evaluated.